Okay, so today we're going to be doing 6.6, so the last lesson of Unit 6, where we're going to talk about solving for quadratic trig equations. So just some strategies for solving some quadratic trig equations is to solve a quadratic trig equation, we often factor it and then solve the resulting two linear trig equations. If it is not factorable, you can use the quadratic formula. So yes, if you do have a trig ratio or trig equation that can't be factored, you can use the quadratic formula. You just have to use let statement so that you don't confuse yourself. So you may need to use the Pythagorean identity, compound angle formulas, or double angle formulas to create a quadratic equation that contains only a single trig function whose arguments all match. And to check your solutions, you can use a graphing calculator by graphing both sides of the equations and then finding the intersection points, or create a single function of the form f of x equal to 0, graph it, and determine the zeros. So the first example we have here is we want to solve each equation for x in the interval x is greater than 0 but less than 2 pi. So again, we have to respect the domain that we have given to us so that we can have the appropriate answers. So the first example we have is sine squared x minus sine x is equal to 2. So we're going to move the 2 over, which gives us sine squared x minus sine x minus 2 is equal to 0. So now we have a quadratic function where our product is -2 and our sum is -1. So these two numbers will be -2 and +1. So we get sine x minus 2 bracket sine x plus 1 is equal to 0. This means our two roots are sine x is equal to 2 and sine x is equal to -1. However, there is no angle that gives us a sine value of 2, so therefore this is inadmissible, so it does not count towards our solution. However, sine x is equal to -1 does count because sine gives us a value of -1 when x is equal to 3 pi over 2. And again, you can use the unit circle to help you figure out these solutions. Okay, so I suggest you have your unit circle with you at all times when you're solving quadratic trig functions. For question B, we have sine squared x minus 1 over sine x minus 1 over 2 sine x minus 1 over 2. So what we can do to help us get rid of the fractions is multiply both sides by 2. So you get 2 sine squared x minus sine x minus 1 is equal to 0. Now we're going to have our let statement. We're going to let a be sine x. So we're left with 2a squared minus a minus 1 is equal to 0. So again, our product is equal to -2, and our sum is equal to -1. So again, those two numbers are -2 and +1. So when we factor out, we're left with 2a plus 1 bracket a minus 1. And now all we have to do is sub in sine for a. So we get 2 sine x plus 1 times sine x minus 1. Which means our first solution is sine x is equal to -1 over 2. And our second solution is sine x is equal to 1. So using our unit circle, at what radian measure does sine x give us -1/2? And that is when x is equal to 7 pi over 6 and 11 pi over 6. And now we have to ask ourselves, where does sine x give us a value of 1? And that happens at x is equal to pi over 2. So x is equal to 7 pi over 6, 11 pi over 6, and x is equal to pi over 2 satisfies the equation sine squared x minus 1/2 sine x minus 1/2 is equal to 0. So again, like I said, all we're using is a unit circle. So we're looking at our unit circle. For example, in question B, we're finding out where sine x gives us -1/2. We will use our unit circle. And same thing with sine x is equal to 1. Use our unit circle to determine where sine x gives us a value of +1. Remember, when it comes to unit circle, we have x and y coordinate. Remember, our x is cos and our y is sine. Now we're going to move on to example 2. So example 2 says solve for x in the interval -2 pi and 2 pi for the equation cos squared x minus 3x minus 3 sine squared x is equal to 1. Oops, wrong page. So here, as you can see, with cos squared x, we have an identity. So we know cos squared x is equal to 1 minus sine squared x. So now what we can do is just simplify our equation so that we have everything in the same term. So because cos squared x is equal to 1 minus sine squared x, that whole equation is going to be in terms of sine now. So you get 1 minus sine squared x minus 3 sine squared x is equal to 1. So now all we're going to do is simplify everything. So we're going to leave the sign on one side and the numbers on the other side. So we get -4 sine squared x is equal to 1 minus 1. So you get -4 sine squared x is equal to 0. Divide both sides by -4. You get sine squared x is equal to 0. And that is pretty much the solution right here. So now we have to figure out at what angles does it give us the expression sine squared x is equal to 0, or it's the same thing as finding sine x being equal to 0. So if we look at the unit circle, we know that sine gives us a value of 0 when x is equal to 0, pi, and 2 pi. But because of our domain or our interval that we have to focus on, our solution also has to include -2 pi, pi, and then what we had above. So this equation is satisfied when x's are equal to -2 pi, pi, 0, positive pi, and positive 2 pi. So as you can see, it's not that difficult so far, but we're going to get into an example where we're going to have to figure out a way to change the equation so that it can work in our favor. So example 3, we have 1 plus sine x is equal to cos x. We want to solve for x in negative pi and pi as our integral. So as you can see with this example, we really have nothing that we can work with, mainly because we cannot change sine x and cos x to give us something that is similar. So we are going to have to do something else or improvise to help us find out the solution. So remember, with algebra, whatever you do to the left side, you also have to do to the right side. So what we're going to do is you're going to square both sides. Okay? And then I'll explain after why some solutions may not work. Okay? So when we expand the first bracket, we get 1 plus 2 sine x plus sine squared x is equal to cos squared x. And from our previous example, we know cos squared x is just 1 minus sine squared x. So we can change it into 1 minus sine squared x. We have 1 plus 2 sine x plus sine squared x is equal to 1 minus sine squared x. And now all we're going to do is we're going to bring the right side over to the left side. So we get sine squared x plus sine squared x plus 2 sine x is equal to plus 1 minus 1 is equal to 0. So the 1's cancel out, and we're left with 2 sine squared x plus 2 sine x is equal to 0. And like any algebraic problem, you're going to factor out the common factor, which is 2 sine x. So you have 2 sine x is equal to 1 plus sine x is equal to 0. And now we have two sets of roots. So our first root is where sine x is equal to 0. And the second root is when sine x is equal to negative 1. So now again, all we're doing is using our unit circle to figure out where sine of x gives us 0. And based off the previous question, we know that sine x is equal to 0 when x is equal to negative pi, 0, and pi. And sine x is equal to negative 1 when x is equal to negative pi over 2. However, because we changed the nature of the question, we need to check that all roots satisfy the original equation. 1 plus sine x is equal to cos x. So we need to check. So first let's sub x is equal to negative pi. And remember, we're referring back to our original equation. 1 plus sine x is equal to cos of x. So let's sub in negative pi for x. So you get 1 plus sine of negative pi is equal to cos of negative pi. So you know sine of negative pi gives us just 0. So we get 1 plus 0 on the left side. And cos of negative pi gives us negative 1. So you get 1 is equal to negative 1, which cannot happen. Therefore, negative pi as a solution does not work. Okay, so if x is equal to negative pi doesn't work, then we need to check if x is equal to positive pi doesn't work as well. So we get x is equal to pi. So we get 1 plus sine of pi is equal to cos of pi. So we know sine of pi just gives us 0 again. However, cos of positive pi gives us negative 1. So we get 1 is equal to negative 1, which again cannot happen at all. Okay? So the roots of x is equal to negative pi and positive pi do not work. However, when we sub x is equal to 0, it does work because sine of 0 is 0, so you get 1 plus 0 on the left side, which is 1, and cos of 0 already gives us a value of 1. So 1 is equal to 1, therefore x is equal to 0 works, and x is equal to negative pi over 2 works, because if you sub it into the equation, it gives you left side is equal to right side. So when we change the nature of the equation, it gives us roots that do not work. And when we do this, these are called extraneous roots. So these are the roots that we obtain when we change the nature of the equation being solved. So in this case, we needed to square both sides, and by doing that, that changed the nature of the equation, okay? And in turn, when we did that, it gave us extra roots that didn't work. So therefore, the only solutions in this question are x is equal to 0 and x is equal to negative pi over 2. So at any point, you can't simplify the equation by making all terms be the same. You can square both sides if that helps you, but remember at the end you need to check that all the solutions that you got are correct. And if any of the roots do not satisfy the original equation, they are called extraneous roots. Okay, so let's move on to the next question. So we want to solve the equation using sine x times cos x is equal to 0 for x over the interval of 0 to 2 pi. Okay, so let's just basically treat this as a typical equation. So let's say let A be sine x and let B be cos of x. So in turn, we have A times B is equal to 0. And when we have this as a regular quadratic or just a regular algebraic equation, our solutions are A is equal to 0 and B is equal to 0. And now we sub in our functions back in. So we get sine x is equal to 0 as a solution, and cos x is equal to 0 as our solution. So using our unit circle, we know sine x is equal to 0 when x is equal to 0, pi, and 2 pi. And we know cos of x is equal to 0 when x is equal to pi over 2 and 3 pi over 2. Okay? So remember, all the solutions have to fall within the interval we are given, which is between 0 and 2 pi. Therefore, x equals 0, pi over 2, pi, 3 pi over 2, and 2 pi, because all of these solutions fall under our interval of 0 and 2 pi. And now we are going to do our last example. So we're going to solve the equation negative 2 cos 2x is equal to 2 sine x for x over the interval of 0 to 2 pi. So what we need to do first is get everything under the same form. So if you want to turn everything into cosines, turn everything into cosines if possible. If you can turn everything into sine, turn everything into sine. So as you can see here, cos 2x, we have our double angle formula. And cos of 2x, remember, is 1 minus 2 sine squared x. So we're going to get negative 2 times 1 minus 2 sine squared x is equal to 2 sine x. And now what we're going to do is factor in the 2 into our brackets. So we get negative 2 plus 4 sine squared x is equal to 2 sine x. We're going to move the 2 sine x to the left side. So we get 4 sine squared x minus 2 sine x minus 2 is equal to 0. And what we need to figure out is if there is a common factor. And what we can do is factor out a 2. So we're left with 2 sine squared x minus sine x minus 1 is equal to 0. And now what we need to do is factor it out using sum and product. So we know our product is equal to negative 2, and our sum is equal to negative 1. And this is something we've already seen. So when we factor it out, we get 2 bracket 2 sine x plus 1 times sine x minus 1 is equal to 0. So that means our two solutions are either sine x is equal to negative 1 over 2, which is what we already had before in the previous question, and sine x is equal to positive 1. So now using our unit circle, we figure out at what angle does sine x give us negative 1 over 2. And this gives us negative 1 over 2 at x is equal to 7 pi over 6 and 11 pi over 6. And for sine x is equal to 1, that only happens when x is equal to pi over 2. So if all of these three fall under our interval, then we can use all three as our solution. And in fact, all three of them fall under the interval, so all three are included in the solution. So therefore, x is equal to pi over 2, 7 pi over 6, and 11 pi over 6. So as you can see, this lesson wasn't pretty long. All you're doing is taking things you learned from the polynomial unit and applying it to quadratics. The only difference is that if you don't want to confuse yourself, you can use let statements. So for example, if we had 4 sine squared x minus 2 sine x minus 2, and you don't want to see the sine x's there, just have a let statement. For example, you can let a equal to sine x. But remember at the end, you just have to sub in sine x back for a. Okay, so this is pretty much it. Remember, you have your assessment tomorrow for Unit 5, your quiz for Unit 6, and your assessment for Unit 6 will probably be all next week. We're going to be starting logs on Friday, and that's pretty much it for this unit. And then we're pretty much on pace to finish the course within a good, timely manner. So again, if you have any questions, feel free to ask me. I'm available at any time. Just remember, not after 2:20, preferably. But yeah, so if you have any questions, ask me. Hopefully you find this video pretty helpful. So other than that, you guys can start doing the homework for this lesson and start preparing yourselves for your assessment tomorrow.